All right, physics students, we're going to wrap up the idea of momentum and impulse with this video, and I'm going to talk to you about a very, very important concept in physics. It's another conservation law, and it's the conservation of momentum. Okay. Now remember that since momentum is a vector, the total momentum of a system is basically the sum of all individual momenta of the objects of the system, just like it was with forces. Remember we said the sum of all forces was force 1 plus force 2 plus force 3 and so forth. We call that the net force. Now we can think of the net momentum in terms of a vector quantity. Now, like forces, the x and y components themselves are independent. So, momentum, like forces, momentum is concerned in the horizontal and the vertical components. Okay, so all that work that we did with sums of vectors and the sum of all forces and all that kind of stuff with vectors, that doesn't go away. Okay, so now in an isolated system, meaning it's a system where no other forces are acting, you're only considering one particular object or two or three objects or whatever, the total momentum is always the same, and this is called conservation of momentum. And I don't know if you've ever seen one of these deals. Okay, this is called Newton's cradle, and it's an interesting way, it's an interesting demonstration of not only the conservation of energy, but the transfer of energy and the conservation of momentum and the transfer of momentum and that sort of thing. Okay, so notice that in a perfectly frictionless environment, if the system really is isolated, that is to say that friction isn't acting or no other non-conservative forces, okay, the balls on the ends will go up the same height every single time. Okay, so that's kind of a neat little curious physics item there. Now, the conservation of momentum holds all the time, even if the system, or for sure if the system is isolated, not even if. The system has to be isolated in order for that to hold, neglecting all other forces. So when objects collide and bounce off each other, these are called elastic collisions. When objects collide and stick together, these are called inelastic collisions. And when objects explode apart, not a collision, but it's like a spring between carts. And in this case, you have something breaking up into different masses, and we'll talk about that in just a little bit. In reality, most collisions are a combination of elastic and inelastic. Okay? So generally, the conservation of momentum, when we're using it for problem solving, is of this form where m1 v1 is the momentum of the object 1, m2 v2 object 2, m1 v1 prime, v2 prime. The primes here indicate after the collision. So again, we're assuming that the masses don't change. So m1 over here is still the same as the m1 after, and the prime indicates afterwards. Okay? Again, this is a statement of the conservation of momentum. This is how we're going to use it when we actually solve problems, and we'll do some demos in class. Okay? Now, the types of collision are actually classified by whether kinetic energy is conserved. That's how we decide what kind of collisions we have. The first kind is an elastic collision, and these are when objects collide and bounce off of each other. Okay, so here's their initial position. M1's over here, M2 is over here. They bounce, and either of them recoil in the same direction from whence they came. The total kinetic energy of a system after the collision, in an elastic collision, is exactly the same as the total kinetic energy before the collision, and momentum is conserved, so the initial momentum equals the final momentum. Now, inelastic collisions are very, very different. These are when objects stick together and then they either stop or they move along with a final mass equaling the sum of the two masses of the things that hit each other in the first place. Okay? What's important to note here is that the total kinetic energy of an inelastic collision is not conserved. The total kinetic energy after the collision is not the same as the total kinetic energy before collision. In fact, afterwards it's less because we've lost some energy in that collision. Now, momentum, however, is conserved, so we can use the previous statement of momentum to deal with elastic or inelastic collisions. Now, many of the concepts of momentum that we study are actually common sense. So, for example, if you have two balls of the same mass, this one's going faster, this one's going slower, okay? When they collide, basically the red ball sort of acquires some of the energy of the purple ball, okay? And it ends up that the speed of the purple ball is less than what it was before, and the speed of the red ball is greater than it was before, okay? So to me, that's common sense just by being alive and playing with objects as a kid and seeing how things bounce off one another with different masses and different speeds, okay? And if two objects stick together, you would expect that their speed would be less, and we're in fact going to find that out analytically. Okay. Now it's important to understand how balls bounce and what this means in terms of momentum and energy loss. So for a first example, imagine that you had a small steel ball, like a ball bearing, and you dropped it on a hard floor. Now, that ball is never going to come up exactly to the same height from whence you dropped it, but it comes pretty close, okay? And if you have like one of those crazy balls, like you get at the circus, the ones that bounce really high and all over the place, those come up almost to the same height, okay? Now, if it does come back up to the same height, it is elastic. In fact, it's perfectly elastic because energy and momentum are conserved. And you know that energy is conserved because it comes back up to the same height. It hasn't lost any kinetic energy in its collision with the floor. We call that elastic. Now, example 2. Imagine if you take a basketball and you partially deflate it and you drop it on a hard floor. It's going to bounce back up a little bit, but nowhere near the height from which it was dropped, okay? Therefore, it's lost some kinetic energy in the collision with the floor. We call this inelastic, okay? Now, if you completely deflate the basketball and drop it on a floor, it's just going to stick to the floor. It's not going to bounce up at all, okay? All of its kinetic energy has been lost in the collision with the floor, and we call this completely or perfectly inelastic, okay? So those are the different kinds of deals that we have going on here with momentum. Okay, here's your first conservation of momentum problem. Okay, you'll find that there's a very common strategy, like kind of a recipe that we use every single time that we solve these problems, and you'll get it very quickly. It's writing a lot of variables and doing a lot of algebra, but I know that you guys can handle that. So take a look at example 7. Remember the conservation of momentum, and try this one on your own. Okay, so these cars stick together, so this is an inelastic collision, okay, but momentum is also conserved, okay, even though energy is not, all right? So this is the sum of the momenta before, okay, m1 v1, m2 v2, okay, and I'm saying that cart 1 is the 60 kg cart, and cart 2 is the 30 kg cart. That's what I'm saying here. Is that right? Yes, correct, okay, all right. Because the 30 kg cart is at rest, its initial momentum is 0, so we can cross that out of this equation right away. Okay. Now that's equal to the momentum of cart 1 after plus the momentum of cart 2 after, denoted by the primes. Okay. And then all you got to do is you just solve for v prime. Now what I'm doing here is I'm noting that v1 prime and v2 prime are the same because they stick together and they have the same velocity. Okay, so m1 v1 equals the sum of the two masses, which is now greater than it was before, times v prime. So v prime is the speed or the velocity of this big 90 kg lump of cart. Okay, so noting that, you solve for v prime, and I got positive 2 meters per second, positive indicating that it's going to the right, okay? Now, the kinetic energy loss, well, you just figure out the kinetic energy before for the entire system. Here's before, okay? And here's the entire system after. Again, you see my subscript 2 and my superscript prime, okay? I got 270 before and 180 afterwards, which means that there's a change in kinetic energy of 90 joules in this inelastic collision, okay? Here's another example, okay? We have two blocks of the same mass. One is at rest, the other one is not, coming in with a velocity, with a speed v. And basically, I'm asking you to show that the final velocity of the blocks when they're stuck together are 1/2 of v, okay? So kind of a similar case as example 7, but without numbers, okay? Again, conservation of momentum, noting that block 2 has no momentum initially. Initial, final. Initial on the left-hand side, final on the right-hand side, okay? You solve for v prime, you get that v prime, which again is v1 prime and v2 prime, it's the same thing, that equals 1/2 of v1. So, proven, okay? All right, try this one. It's going to get more interesting. This one's about ice skaters. Go ahead and read this one and try it on your own. Okay, so we have two ice skaters. One has less mass than the other. M1 is a woman and M2 is a man. Okay, the woman moves away with a velocity, and they're initially at rest. Okay, so the total momentum of the system is 0. They push off of each other. You know by common sense that they're not going to be going the same speeds, right? Okay, the man will be going slower because he has more mass. I hope that you have a sense of that. So let's see, conservation of momentum before the whole system is 0. Okay, And then all you do is you solve for v1 prime, okay? And v1 indicates the velocity or the speed of the woman. It's negative 1.5 meters per second. The negative sign here just indicates that she's going in the opposite direction of the man who is going away. And this should actually read, sorry, this should actually read man. The man moves away with a velocity v2 equals 2.5, okay? Anyway, the negative sign indicates that the woman and the man go in different directions, okay? Okay, here's a slightly more, this is a similar one, not too difficult. Try this one. Okay, by the conservation of momentum, note that ball number 2 has no momentum, so it's 0. Okay, that's equation 1. Conservation of energy, that's equation 2. Again, the initial kinetic energy, is 0 for ball 2. Okay, I'm going to use both of these equations to solve this. Okay, I know that ball 1 rebounds with a particular speed. I can either use 1 or 2 to solve. Okay, by using 1, the conservation of momentum, I get 2.38 meters per second. Okay, just follow my algebra. Pause it if you need to do the algebra yourself. I recommend you do it on your own scratch paper. Using 2, I get also 2.38 meters per second. So what we end up doing is we end up using the conservation of energy and the conservation of momentum in conjunction. And if you're not given one of the final speeds, it becomes a lot more difficult algebraically. Usually in the IB, they will give you that. So I wouldn't necessarily ask you to do such a difficult problem. I'll always give you one of those variables, and then it's a little bit easier. Okay. Okay, this one's a lot more difficult, and I want you to spend some time working this one. I'm not going to do the algebra for you, but I'll set it up for you. It's as similar as the other one. Now I have 2 blocks. One is twice as massive as the other. They're coming in at the same speed. They have an elastic collision. They recoil, basically asking you to find that the black one has v over 3, and the blue one has 5v over 3 final speeds, okay? Conservation of momentum, conservation of energy. I rearrange these equations as such. I have 2 equations and 2 unknowns, and you just need to prove that v1 prime is v over 3 and v2 prime is 5v over 3, okay? So good luck with that. If you get stuck, ask me to do it in class. I'll be happy to do it, okay? Okay, here's a past paper question. Read this one carefully and then do it on your own. Okay, so an inelastic collision. I'm going to let M1 equals the mass of the pellet and M2 equals the mass of the clay block. Conservation of momentum, okay? This is 0. This is the clay block initially, no momentum. All you do is you solve for V1 prime. I get 0.016 meters per second. Make sure you can understand that solution, okay? Here's an example of something exploding into different masses, okay? Try this one on your own. Remember, conservation of momentum is what you're going to use to solve this problem. Okay, letting M1 be the big piece, the 100-gram piece, and M2 equal the little piece, which is the 20-gram piece. By the conservation of momentum, before the whole thing had no momentum, because even though it was 120 grams, it had no velocity, so its momentum was 0. This means that this value plus this value equals 0. And all you got to do is solve for V2 prime, and I get negative 25 meters per second, indicating that it's going to the left, opposite of the 100-gram mass, okay? And does your common sense tell you that the little one would be going a lot faster? Definitely. Well, it's 5 times faster because its mass is 5 times less, okay? Okay, I want to very quickly talk about force time graphs, and we'll wrap up this video, okay? Remember when we with work, we found the area under a force displacement graph, and that was our work. Well, similarly, if we graph F and T, or F and delta T, we end up with what's called a force time graph, and the area under the force time graph is the impulse, or the total change in momentum by the impulse momentum theorem, because F delta T equals delta P, okay? In this case, this is not a case of the force being constant, obviously, okay? So we need to use a graph and find the area under this graph, which is, if it's curved, as usual without calculus, it becomes a pain in the rear end, okay? I believe almost all of the force time graphs you'll be given in the IB will be straight lines, or they'll be curves that'll be fairly easy to estimate, okay? So here's an example of 2 different force time graphs graphed on the same axes. The areas under these 2 curves are the same, so the force acting for a shorter time must be larger on average. Remember, because if the area under the two curves are the same, it means that the change in momentum is the same. So these two objects, the one with the bold line stopped more quickly, but it had the same mass, okay, and the same velocity, okay. Now, the one that's in the lighter, the thinner line, it took a longer distance to, or not a distance, a longer time to stop, so its average force was less. And I've drawn on here the red line corresponds to the approximate average force by sight of the bold face graph, and the blue one is for the lighter graph, okay. Now, imagine a ball falling on a concrete block in a trampoline, okay? The more force, the harder the surface. When the ball hits the block, okay, it contacts the block over a much shorter time, so therefore the force is greater. Whereas a trampoline, it kind of comes and it bends a little bit, and delta t is greater, so therefore the force is less. That's why we have fun as kids jumping on trampolines and not jumping on concrete blocks, because that would really hurt, right? That would impart a really big force to us. And it also goes back to why it's better to have a flower pot break on your head than bounce off your head, okay? All right, let's just sort of analyze this graph here, okay? In this particular graph, the area under the curve, which is the impulse, I'm approximating it to be 2.8 kilogram meters per second. I'm saying there's about 14 major squares. Each major square is about 0.2 kilogram meters per second. That's a rough estimate, okay? The time interval over the force x, okay, is about 6.8 milliseconds by my reckoning, okay? The momentum change over the time interval is the area under the graph. Don't be tricked. That's the impulse. That's F times delta t. That's the same as the area under the curve, what I found in this part, so that's 2.8. The maximum force is clearly 1,000 newtons, and the average force, this is the trickiest part of this, note that F delta t is the impulse delta p, which we found before, okay? Since delta t is 6.8 milliseconds, all you got to do is you just divide 2.8 by 6.8 times 10 to the minus 3 to get about 412 newtons. And of course, analytically, that matches very well with what it is visually. That's right in this range right here, okay? So it works. Physics is great, okay? Okay, last example before we end this video and this topic, okay? Here's a nice straight or triangular force time graph. Go ahead and solve this problem before you see my answer. Okay, for the impulse, simply the area under the graph. Notice that it's not symmetric about that line. There's more area over here than there is over here. I got 0.875 kilogram meters per second. If the mass of the object is 20 grams, I got a change in velocity of, what did I get? 43.8 meters per second. So a pretty big change in velocity. Now, we don't know what the body is, so we can't really comment on that. And I want you to also note that the average force, by using the same method I did before, okay, I'm dividing the impulse, or I'm dividing the change in momentum by this total time interval over which the collision took place to get 2.5 newtons. And again, visually, you see how that matches with what you would guess the average force to be.